Section 5.1 is going to go back over kind of a recap of some things we've already done in Chapter 4. So some fundamental identities. And we've already looked at this one. Sine of x is the same thing as the complement or cosine of the complement of x. So I'm going to give you a little visual proof of that one. We've looked at that in a couple of ways, but let's begin with sine of x. The sine of x, we know it starts at 0, 0. At pi over 2, we're up to 1. By pi, we're back to 0. And negative 1 at pi, 3 pi over 2. And by 2 pi, it finishes up this cycle. So something like that. Now to look at the complement for cosine here, I'm going to do our little trick where we set this equal to 0. Kind of think about where cosine normally starts and where this one's going to start. So this one will start at pi over 2. Now cosine, typically if you do cosine of 0, you get 1. So at this point, at pi over 2, this graph, the y value is going to be 1. So I'm going to put a point down here, pi over 2, 1. So far looking pretty consistent with the sine graph, even though it's only 1 point. And then the next time here, I'm going to take the pi over 2 minus x. Now, typically we'd set that equal to 2 pi next, but with the negative x going on here, it'll actually put the value way back this way, which you could try it, but you'll see what happens. So I'm going to try negative 2 pi. If that seems really bizarre, it'll check out in just a second. But if you went back a full cycle, if cosine is typically at 1 and 0, negative 2 pi would also be at 1. So let's work this out and see what happens. So I'll add 2 pi to both sides, add x to both sides. And if I want to make 2 pi into something out of 2, it's going to be 4 pi over 2. So at 5 pi over 2, that's the next time the cosine will be back to 1 for the y value. So I went ahead and had 5 pi over 2 over there ready to go. Now cosine, once you start at 1, you go back to 0, then down to negative 1, back up to 2 pi. You can also go back this way. So that's definitely looking just like sine. And again, that's just sort of a little, we'll say quote unquote proof, but there's a visual way to see the graph. It's definitely the same thing. And going back to even and odd functions. So if something's even, then if we plug in the negative version for x, we're going to get the exact same y value out that we began with. And if something's odd and we plug in the opposite x value, then we end up with the opposite y value. So that's going to be our test. I'm just going to kind of do this visually. So let's take a look at the sine graph. The sine looks something like this. So if I pick any x value and look at the y, if I pick the opposite x value, it looks like the y is going to be the exact opposite. Now we could test some points and verify that completely, but the sine function is going to be an odd function. Okay. So algebraically, it looks something like this. You would say sine of negative x and see what it equals. And you could try some of your unit circle values and see what it came out to be. But when you check that out, whatever x you put in there, if you make it negative, you're going to get the opposite y value out. So sine is definitely an odd function. I want to leave sine up because we're going to eventually get to cosecant. But a cosine function is going to look something like this. And it's centered around the y-axis. So if you pick an x value and look at the y that goes with it, if you pick the exact opposite x value, you're going to get the exact same y value back out. So that's by definition an even function. And we can do something with the algebra like that if you want. Cosine of negative x is going to end up being the same thing as cosine of x. Again, pick any value in the unit circle, try it and see what happens, but that's going to always be verified. And for a tangent graph, at negative pi over 2 and positive pi over 2, you're going to have some asymptotes. And in between, it basically looks just like an x cubed function. So that one's going to be odd. You pick any x, see where it comes out to be y. If you do the opposite x, you get the opposite y, so that one is an odd function. Okay. All right, on my list, I went to cotangent next. Now cotangent has an asymptote at 0 and then another one at pi. And it kind of goes the opposite direction. It goes downhill. It's like a negative x cubed. But then if you put another cycle over this way, at negative pi, you have another asymptote. And you have the same shape happening. If you pick any x value and see where it ends up, and then do the negative x, you get the exact opposite y. So that one is also odd. For cosecant, we're just going to go back to the sine graph. And we're going to have an asymptote anywhere the sine was 0. And it's going to have these sort of parabola-ish shapes. And really, it's going to follow the same logic as sine. Anywhere that you pick any x, see what you get. You pick the opposite x, you get the opposite y. So that's also going to be odd. Secant, it's going to use the cosine function. And similar logic, anywhere you have an asymptote, or sorry, anywhere you had 0, you're going to have an asymptote now. Sort of parabola-like shapes. You can see the symmetry there, so that one's going to be even. This whole even-odd thing probably doesn't seem like it's going anywhere quite yet. And it probably won't mean a whole lot until you get to calculus next year, but you'll be glad that you had a pretty good understanding of these even and odd functions, because these will eventually become something called a Taylor series. And they'll also define some other important series in calculus, so it'll be something that'll be worth your time eventually. All right, factoring expressions that have trig functions built into them. I think U substitution is the best way to go with things like these, and I'm going to stick to the general rule that I take the middle term and make U whatever's there. So U will be tangent of x. And really the way to check to see if that's the right thing to do is just see if you get U squared here, just U here, and a constant. And if that happens, then we should be good to go. So there's what it would look like if I made that substitution. And it's got U squared, it's got U. Let's just make sure everything verifies. If I put tangent here, I get tangent squared, that's good. Put tangent here, that's tangent. So it looks like we're good to go. So now I just need to factor it out. We'll do a little shortcut. Factors of negative 12 on top, then add to 1 on the bottom. That's going to come out to be 4 and 3. Just don't forget to divide by that leading coefficient of 4. So I'll end up with U plus 1. Simplify that. And I'll pull that, oh, this was supposed to be negative, sorry. And then 4u minus 3 for the other factor, because we did a little trick there, we pulled that 4 out front. And then put the tangent back in for u. So tangent x plus 1 and 4 tangent x minus 3. Final example for the day is a verification. Remember, verification, you pick one side and work it out until it becomes the other. You can pick either side you want here. But I'm going to go ahead and go with the left-hand side. It's completely up to you when you get to a verification how you want to go. Now, I'm not going to write this as an equation because I'm just taking this side and I'm going to simplify until it turns into that. I just want to show that this can be derived into the other side. Now, I'm going to have to use a little corollary here. So one of our identities, we know that 1 equals sine squared x plus cosine squared x. And that's going to be pretty useful, and you just have to kind of get used to where you're going. Look what the best thing to do is, because a lot of these, you can kind of hit dead ends. You can try something that's true, but then it doesn't really lead to where you want to end up. So I want something that's going to be 2 cosines over here, and I want sine to be gone. So this seems like a logical choice. I want to solve for sine squared, so I can substitute something in there that only has cosine. And that's sort of a little hint that you look for little hints like that all the way as you're doing problems like these. So again, I'm going to solve this for sine. So 1 minus cosine squared x is equal to sine squared x. And I'm just going to leave it at sine squared x because this is sine squared. I can just make the direct substitution there. So because that's true, and I'll just go ahead and put it in parentheses. I'm going to, again, substitute sine squared x with 1 minus cosine squared x. And then I'll just fill in the rest. Now this is minus, be careful with that. That's going to change this sign to a minus, change this to a plus. So to wrap it up, we got cosine squared x plus another cosine squared x. And then minus 1. And that's going to be exactly what we wanted to end up with, so that's it. That's the verification.